Hi guys, and welcome to this session. Today is November 8th. We are, I think, in week 13 now. We have quite a few topics to cover this week. Actually, we have 4 units, and we still have a long way to go, honestly. We still have 5 units next week. Then we have the week of Thanksgiving, and we have several units after that, still finishing them. So we're going to go to really the week before the finals, really, when we have our when we finish all of the materials that need to be finished. So this is basically how things look out right now. We will have a week of for Thanksgiving. Also, there was an announcement today about the Thursday sessions. There will be no more live sessions on Thursday. There will be recorded sessions. So I will go through those things. Now, it's still that if you still have questions or if something is not clear, please reach out to me. Especially in terms of assignments. In terms of homework, I think we're probably, for the most part, we're done with the main bulk of the assignments. So we still have the discussions, and we still have also quizzes. We still have another exam that is coming after Thanksgiving. Actually, it's going to be during the final week. So that's basically in terms of all of the content for this class. So we moved from the solar system. Today actually marks the start of talking about stars. So today is the beginning of the universe section of this class. So we've been talking mainly, the first part dealt really with the tools astronomers use to determine positions of the celestial objects in the sky and basically track down some of the familiar objects like the moon, the sun, and the day and night, and all of these things and their influence on how they are basically categorized. Then the second part really dealt with the solar system. We spent a little bit of time, honestly. We didn't really go in depth about all of the planets. We did some planets in depth because we sampled some. And then we moved to started building our tools basically to move to the stars. So we talked about light because light is the main tool that we use to study stuff in the sky, to study objects in the sky. And even a telescope really collects light. So it's an instrument that collects light. So we did a little bit of mainly the properties of light when it comes to their electromagnetism part of it. We didn't really spend a lot of time on the optics part of it, which is actually important too, especially if you're going to understand how telescopes work, for example, and how cameras function and things like that. So that's basically where we were, and then we moved to the sun. We spent a little bit of time talking about the sun, and now the topic today, as I was saying, we're starting the stars. So we're going to be spending a little bit of time on the stars, their classification, how we identify them, and their groupings, how we locate them, and so on and so forth. After that, there are some special stars, or at least some stages of the stars that we need to understand, namely 3, the white dwarfs, and also the neutron stars, and finally black holes. Black holes is really a final stage of some of the most massive stars. Then after that, we're going to start talking about basically galaxies and cluster of galaxies, and try to understand where the universe, its history, and where it's headed, basically its future. And then at the end, we're going to spend a little bit of time talking about life outside of the solar system, basically outside of the Earth to begin with. So because the only place that we know has life in it is the planet Earth. That's the only one that we know. But we can build, based on what we know about this life on Earth, what is the possibility for life in the solar system, and that is what is the possibility of life outside of the solar system, just in our own galaxy. I mean, most likely in other galaxies there is life forms, but we will never, impossible to even communicate with those life forms outside of our own galaxy. I honestly should not really be saying never, because there is something that probably could be achieved through wormholes, where potentially could end up in other galaxies. So without getting into some sci-fi, That's basically with the stuff that we'll be covering into this in this class, and that's the whole idea. So without further ado, just to get into the topic, let me share with you the units for this week. We're going to cover 2 units, namely 56 and 57. And as I was saying, the units for the other 2 units of this week will be recorded and posted on Canvas in the session where it says Thursday session. Remember, we used to do live sessions Tuesday, Thursday, and because basically of the attendance and the fact that this is supposed to be an online class, so I'm cutting it in half in terms of live sessions, but I still be recording the topics basically for you guys, and so that you can watch them later on. And you still are required to watch them and basically send any feedback and everything else to in comments and the discussion sessions and so on and so forth. So let me go into Unit 56. Let me start it from the beginning. So Unit 56 talks about basically the spectral lines that emanate from the stars in general, and how the surface temperature of that star affects the spectral lines, and how is the distribution also of matter around the star also affects those spectral lines. Obviously, if I don't have hydrogen in the atmosphere of the star, then I will not have, or if the star is poor in hydrogen, then I will have basically a less absorption lines for hydrogen. If the star has an abundance of helium, for example, then I will have more spectral lines for helium. So the amount of matter that is basically in the atmosphere of the star matters. So if the star, for example, does not exhibit neither of hydrogen and helium, it may have, or at least it may have a combination of the two, or it may have other elements that are clear in the spectral lines, for example, carbon, okay? So this is basically what we're going to be talking about. We talked extensively about Wien's law, and this is important because we're basing everything off of it, honestly, trying to find the wavelength as a function of temperature, the surface temperature. This is a very important law because it really helps us find the temperature, or if I know the temperature, I know the maximum wave. So that's basically the idea behind it. So Wien's law is a very, very important law that really plays a major role in the whole thing. And that's the whole idea behind it and where the maximum is. So the fact that I was saying a star, for example, is maxed around the blue, so it's a blue star, or a star that is maxed around the red, or anywhere in between. So there are all kinds of frequencies in between. As a matter of fact, the number of spectral lines, I mean, the frequencies is an infinite number of frequencies, but the spectral lines themselves are finite. They're discrete, actually. So if you look at a given spectrum of any material, whether a star or non-star, doesn't matter, the lines are unique and discrete and distinct, okay, and they depend on the element, okay? Some elements will have different lines and so on and so forth. Now, this could be an absorption spectrum, namely light is leaving the star and it goes through the atmosphere of the star, and then as it emerges on the other end, all the spectrum is there with the exception the one that was absorbed by the elements that are present in the atmosphere of the star. So this is an absorption spectrum. So as opposed to an emission spectrum, which is a little different, you excite the material and then it's going to emit for you waves. So this is the distinction between the two. So again, what we see, of course, of a star, or at least for the sun, is a photosphere. And that what we see actually on the surface of any star is the temperature that is immediately on its surface. As the light is leaving, the photons are leaving, they will encounter the elements in the atmosphere of the star, okay? And depending on basically the temperature of the star, depending on the frequency that are emitted, then you will have different spectral lines, depending on the elements that are present in there. And this is what I was talking about. This is the dark regions in the spectrum are the ones missing. So the spectrum, if there was no atmosphere, should be continuous spectrum. There should be everything is there. But what we notice is there are some missing lines, okay? And each element has a unique signature, fingerprint, if you wish. If you discover that you have certain lines in the spectrum, you know for sure, and you compare them to the chart, well-known charts, then you know that that element is present in the atmosphere of the star. So that's how originally, basically, the idea came about. So when Cannon, she was basically trying to classify the stars based on the intensity, basically, of what is missing. She classified them basically on what she knows, on the stars on the charts that she knows. Okay, some stars, they have an abundance, for example, of carbon, others hydrogen, others helium, and so on and so forth. So that's basically how she went about it. So again, this is Wien's law. Again, Betelgeuse, this is actually, let me see if I can fire one last time, probably. We'll do it. Stellarium here. And see if we can see it actually in action. Obviously, right now it's daytime, so we will not be able to see anything in the sky. But for those sitting in the class of Astronomy 125, so let me change Stellarium, because when it comes up in the full view screen. And I don't want that. Let me put it in the minimize screen. And are you guys looking at Stellarium or not? No? So let me share Stellarium. So again, I'm going to look for this star. The point I'm trying to do is see if I can see colors of the stars, okay? So right now I'm going to remove the atmosphere. I'm in the atmosphere. I'm going to remove the ground and look for Orion constellation. Okay, and maybe it's in here already. I looked for it some other time. So here, even here, you can see the different colors of the stars. Rigel, which is a star in this case in here, appears blue. So, but Betelgeuse appears reddish, and even the color coding in Stellarium gives you different colors. Different stars, like the ones on the belt itself, have different colors too. So all of these different colors, they are actually what gives. So if you see a different color, what you're looking at is different temperature, basically. So this Betelgeuse, for example, is a lot cooler on its surface than Rigel, okay, or Bellatrix for that matter, which are all part of Orion's nebula. So that's, or safe for that matter, okay, because they appear bluer than it. So that's basically bluish than it, I should say. Doesn't this give me the temperature of the star? The surface temperature, that is. I'm looking in here, okay? No. Gives you the magnitude, which is something that we'll be discovering a little later, okay? With the absolute magnitude, which is how bright the star is. The smaller the number, basically, the brighter it is. Some of you who are sitting in Astronomy 125, we're conducting in the lab, actually, right now we're going through the stars in the in this constellation, in this group of stars, I'm sorry, in the Pleiades, and we're trying to measure basically the first thing that we have is their actually magnitude, is their how bright they are, with two different filters. We're using the blue and the visible light, and we're supposed to find basically all kinds of information based on their brightness, okay, based on how bright they are. Anyway, I don't see the temperature in here, but again, if you try to zoom in on that star, it's going to bring it to you as close as possible. This is how it's going to appear. But the point being in here is the text shows you actually the two different stars, or at least a constellation, and tries to compare the different colors between the different stars in the same constellation, and you will see that the colors actually differ, and they differ by the same law that we were talking about in here, which is this one in here. Which is this one. If I put a lambda max and put it on the other side, then the inverse of the temperature. A cooler temperature, lower temperature, will have longer wavelength. So basically, let me rewrite it again. So lambda max, according to this law, is equal to 2.9, which is a fixed number. Okay, so that doesn't change, divided by the temperature. So if the temperature is high, then lambda max is small. Lambda max is the peak wavelength. So where it peaks, here is where it peaks. So this is for a high temperature, 12,000 Kelvin, okay? For something like 3,500 Kelvin, it peaks, so it's a lower temperature, then the wavelength is long. Remember how the spectrum that from the units of the 20s was? This is the visible, so this is the blue, this is the red. The red is a longer wavelength versus the blue. So, and that is basically what's going on in this case. So it's a longer wavelength in here for 3,500 Kelvin, which is cool star. Remember, the sun is 5,800 Kelvin. We learned that some time ago in the previous units on the sun. So this temperature is much, much hotter than the sun, and it peaks. This is where the visible is. It peaks below the visible, actually, and for us, it appears somewhere in the blue. So it appears bluish color. So it peaks in the ultraviolet, actually, this star, okay? But it appears to us in this region. I mean, more so than in the red. Red is less than the other one. So the star appears red, bluish in color, versus this one that is 3,500 Kelvin. 3,500 Kelvin corresponds to a temperature that is in the infrared. So it peaks in the infrared, actually, in a frequency that we don't normally see. We can't see, actually. I mean, James Webb can see those frequencies, but we don't see them. But for us, this is where the visible spectrum is. This is where the light that we can see, more of the red than any other color, than the blue, for example. So the star appears reddish, dark reddish star, versus this one that appears super blue star. That is basically what this thing is. I know in the culturally, something is red is supposed to be hot, and something is blue is supposed to be cool. This is what the culture says, okay? But it's actually the other way around. A hot star is actually blue, and a cool star actually appears red. So that's basically what the two differences are. So hopefully this is clear enough. So again, Annie Cannon, when she classified the stars, she was based on the different elements that she can see, okay? And she classified them based on the spectral lines that she was looking at, and she came up with a classification O, B, A, F, G, K, M. Now we know that O is the hottest temperature of a star, all the way to M, which is the coolest star from her classification. But again, 3 new types were added that are even cooler than M, okay? So the star is classified this way. So what is the sun? The sun is a G star. So the stars, there are stars that are hotter than the sun, and they sit in the O or a B or an A or an F classification. The K and the M are actually cooler stars. So if you're wondering what happened to Betelgeuse, it's actually an M-class star. The sun is a G-class star, okay? So the sun is actually, the temperature is 5,800 Kelvin. Betelgeuse is cooler. On its surface, it's cooler. But remember, Betelgeuse is gigantic compared to the sun. So it will emit still much, much brighter than the sun is because of the facts of its size. You have basically, how should I put it? A cooler light bulb, but it's a huge light bulb. It's going to shine over everything else. That's basically what it is compared to the sun, which is brighter intrinsically because it's a G class classification, but it's still much bigger inside, so it's going to outshine it. So this is the thing to remember. So the sun will emit per square meter more energy than Betelgeuse will emit per square meter. But Betelgeuse has more square meters than the sun does. So that is a difference in the classifications in here. I hope that is clear enough. Obviously, there are different ways of trying to remember this O, B, A, F, G, K, M classification that Canon came up with. And one way is one of the mnemonics that you can remember is O, B, A, fine, girl or guy, depending on your choice, kiss me. Or there is another one, actually, only bad astronomers forget generally known mnemonics. Okay, so that's whatever you can use to remember this classification. Again, for your case, the main thing in here is that this is really from hottest to coolest. Okay, this one you rarely find them in the textbook because those are newer classifications for new kind of stars that are actually brown dwarfs that are sometimes labeled as failed stars, stars that never really ignited in terms of nuclear reactions. Okay, so those are actually super giant Jupiters. Okay, super Jupiters. So it's still like a star because they are by themselves. They may even have planets surrounding them. As a matter of fact, if you look at Jupiter itself, it's a whole system when you look at its moons. Okay, so these are different kind of classifications, but this is the well-known that Canon has put together, and this is the one that is adopted by astronomers everywhere. Okay, sounds good. Okay, very good. Very good, thank you guys. Okay, one thing to remember in here that this classification is not really the whole thing. Within even a group like a G, for example, there are different numbers, okay? For example, the sun is a G2 class star, okay? Because you have numbers from 1, I think, up to like 9, and the sun happened to be a 2, meaning the brightest one will be a G1. Then you have a G2, then a slightly dimmer is a G3, and so on and so forth. So again, the hotter, because this is a range actually, so G is not a given value. G is a range. And it's true for all of these values in here, because O is a range, B is a range, and so on and so forth. So within the same range, this is actually, there is a secondary classification that actually adds a number to it. So for example, the sun is a G2 star. So that you guys have an idea. So one of the things that, and I know I mentioned it earlier, we're looking for example, for stars that can harbor life, you will notice immediately that O, B will probably are not possible, and even the A and potentially, yeah, O, B, A probably are not good because they live very short. They're extremely hot and they will die very young, very quickly, and they will die violently. So it will not really, of the order of 1 million years, it will not give enough time for life to evolve. Like for the Earth, for example, it took almost 4 billion years for life to evolve to the microbial stage, and only in about 500 million years when it exploded, basically, the so-called Cambrian explosion, basically, of life. So only recently, honestly, when life really evolved to the form it is on Earth. So if you're going to have a star that can live only for 1 million years, like even 10 million years or 50 million years, even 100 million years, even 1 billion years is not enough for life to evolve on it. So when we are hunting for life, most likely it's a G class classifications, or even an M or a K. Those are, they live trillions of years. They outlive everything else. So those are the potentially places where you can find life. So we're going to talk about this down the road, but because the sun can live up to 10 billion years, this class G, and that gave enough chance for life to evolve and become the way it is right now. But for stars that are of this classification as O or B or even A, they cannot live too long for life to evolve on them. At least that's reasoning. F is probably a marginal region. Okay. So again, this is the stars. They're all classified and they're all of this. OB, find girl or guy, kiss me. So that's basically how you can remember this. So again, the O stars are, they have a temperature of about 30,000 Kelvin. So they're super, super hot versus the M stars that have about 3,500 Kelvin. So that is basically, and again, as I was saying, it's a range star, a range in numbers, okay? And as I was saying in here, actually, there is a 0, B1, B2, B3, all the way to B9. So it's from 0 to 9, the classifications. This is a secondary classifications within the same classification. So for example, you have an A, it can go from A0 all the way to A9. And the same thing from G0 all the way to G9, and so on and so forth. So this is a secondary classifications within the same group of classification of stars, basically. Again, as I was saying in here, the Balmer lines are the ones that are in the visible range. This is what Cannon actually she was looking at. So this is what Annie Cannon was looking at. She was looking at the spectral lines that you can see. She didn't have the technology, at least at that time, to look at stars in the infrared or the ones in ultraviolet, okay? And that is the actual spectrum that we have. If you look at the hydrogen atom, it has a nucleus inside, which is a proton, really. Then you have an electron. Electron should be really in level 1, okay? Then you have level 2 for the hydrogen. Then you have level 3. 4, 5, 6, 7, and they start superimposed. So I'm not making a mistake. I'm trying to argue in here that the separation between the energy levels starts to shrink as you move up. In transition to the ground state is actually of extreme high energy and does not happen in the visible range. So this we cannot see it. This we see. Any transition from anywhere in here, whether this level or this level or this level up to this level, we can see. Or any transition from here to a higher energy level, we can see it missing. So this is the absorption. And this is the emission. Okay. So again, what's going on in here is that the temperature is too hot for an O classification, or even for a B classification for that matter, for hydrogen to exist in the atomic state. So what she was looking at mainly helium. So she gave them classification depending on the intensity of an O or a B. Then started the ones that are dominated by hydrogen. Now, hydrogen for lower temperatures, A through F, and even to some extent, even in G, actually, all of the lower temperatures, hydrogen can become a gas, normal gas. So the temperature is cool enough for it to have that. So in this case, the spectral lines, they are going to be mainly that of the helium, because the helium has 2 electrons in its outer shell. And so it could exist, because even though the temperature is high enough, but they don't ionize it completely. So there are some spectral lines for helium, but then you can excite one of these electrons, okay? And if you do, you're gonna discover several fine lines for helium. So now, that is for the higher temperatures. Then you start looking at hydrogen, and then calcium and other elements starts to appear later on. So this is how she based her classification. And that turned out to be immediately related to temperature, okay? So that's how the classifications were done. So brown dwarfs later on are given these numbers, this classification, LTY. I don't know anything that you can remember LTY with that. So they are not in alphabetical order. That's the other thing. It's not like A, B, C, D. That's really the. So again, here is the temperatures. As I was saying, it's a range of temperatures, not just a given fixed temperature. So an O is over 30,000 Kelvin. A B is ionized helium, actually, and weak hydrogen in here. So B classification is between 10,000 and 30,000 Kelvin. So these are B stars, and there are a lot of them. So it's a range, about 20,000 Kelvin. And then 7,500 to 10,000 This is actually classification A. It's only 2500 Kelvin, relatively speaking, compared to this 20,000 Kelvin. And then from 6,000 to 7,500, which is another 1,500, basically that is the F classification. Between 5,000 and 6,000, that is the G classifications. Remember, the sun is 5,800 Kelvin. So remember, 6,000 is the upper limit of the G classifications. 6,900 is the second one. 6,000, 5,900, I'm sorry. 5,800 is where the sun is. So this would be a G0, this would be a G1, and the sun is a G2. So there is another group in here that happened to have 5,700, and 5,700 stars will be G3 and so on and so forth. Okay. Obviously, you divide this by 10, and you have to divide this group by 10. So a 30,000 Kelvin will be a B0. But I'm going to take 20,000 and divide it by 10. So in this case, 28,000 Kelvin is actually going to be the B1. 26,000 is going to be the B2, and so on and so forth. So that is how the classification is working. The secondary classification, all the way until you get like 10,000, that is going to be a B9 classification, and so on and so forth. So this is basically how the groupings is working. Then you have the K classifications, which is a little over 1,500. And then you have the M classifications and the L, which is 1,300 Kelvin to 2,000 Kelvin. 700 Kelvin to 1,300 Kelvin. Remember, Venus actually surface is about 700 Kelvin. So this is as hot as the Venus is. Less than 700 Kelvin, this is actually 300 Kelvin is you and I. Okay, so these are super cool stars, if they're even stars at all. So these are planets that are formed, they happen to be so big that probably they couldn't really ignite. So these are failed stars. There is no nuclear reactions happening in them. Okay, so that's basically what's going on with this thing. So this is unit 56. Let me jump into unit 57. We're going to, at some point, develop something called the HR diagram. And we're going to come back to this topic, okay? So let me start back from the beginning. So are you guys looking at unit 57? Yes, no? Okay, very good. Thank you. Very good, thanks. So basically, unit 57 focuses really on the binary systems because they present a present a great opportunity. Because I mean, if you count the stars, let's say for example there are 100 stars, okay, there are billions of stars. Okay, about half of them, 50 of them, are in binary state, meaning that you have two stars next to one another, orbiting each other. So the other 50 are probably single stars, solos. Okay. So if you have a binary system, there is actually another technique that you can use, namely the Doppler effect, because two stars that are actually very close from each other, they're spinning against one another. And we happen to have our nearest neighbors are actually partial binary. Actually, there are 3 stars altogether, but 2 are very close from each other. Alpha Centauri A and B. They're part of a binary. As a matter of fact, if you look at them, they're not visible in the northern hemisphere. They're visible more so in the southern hemisphere. If you look at them, it looks only one star. But if you look very close with powerful telescopes, then you start to see that there are actually binary 2 stars, okay? 2 stars in that system. And they spin, they rotate against one another. So what you do in this case, you can calculate their masses actually by just knowing how fast they go back and forth against one another. So if you know the period with which they rotate, they spin, and if you can have an estimate on their distances, then you can basically have everything that you need to know in order to determine their masses. So binary systems are actually useful piece of information, and they are not solos. They are not few. They are about half the stars out there. There was a project here in San Diego a few years back where they have students, and I'm going to inquire about it and see if I can find information about it, where students from high school all the way to graduate students in astronomy, they work together on projects where they actually select binary system and they start studying, getting all of the spectral lines from it, and they publish actually work. And because there are basically huge number of binary stars, there is always opportunity to find the new binary that was never studied. And because astronomers were soliciting basically the help of the public actually to see if they can collect as much information about stars in general, and this is an easy one to do. All you have to do, I mean, the group that was in San Diego, what they do is they request time on the telescope in Australia, and they designate the star, and the telescope will go for several days, basically collecting light from the binary system. Because a binary will have two stars, one of them is spinning against the other one is moving away, and one is coming down. One that is moving away, its spectrum will look like this. So if this is the hydrogen, for example, spectrum, the spectrum will be shifted toward the red. So these lines will be shifted toward the red. The other one, so you really don't need to stay for months looking at them. All you need is just a few days, okay? To see that there is a shift, there is a motion enough, moving either away from the red toward the blue, because now it's actually slowing down, or moving further toward the red. And the one that is coming down is going to do the exact opposite of what the one that was going coming in. So the other one will actually shift everything toward the blue. And again, if it's slowing down, it's going to move back to where it's supposed to be. And if it's gaining speed, it's going to move further toward the blue. So actually, the study is actually very, very practical one, very useful one, and doesn't require a lot of time on the telescope, basically time. And you could collect enough information, and you will have plenty of data to determine the period, to determine the distances between the stars. And after you do that, then you can determine their masses, and you collect all kinds of information about them. And you also have where the frequencies peak. So you have the information about their luminosity, their temperature, everything else, and you publish. And people basically put a lot of papers in there. And the reason why is, again, because we need as much information as possible, and there is a huge number. Actually, there are more stars than people. Okay, so the possibilities are limitless. Okay, and so again, I was talking about the stars. They orbit usually their common center of mass, called the barycenter. I mean, that's how they refer to it everywhere, not just in astronomy. Okay. So again, when you study their spectral lines, the star that is moving towards us sees its shift. The spectrum is shifted toward the blue, moving toward the blue. I mean, it's still, the red is red, but it's a little bit on the side of the blue than what it should be. Okay. So what you're looking at in here is that closely spaced binary. So in this case, the shift is kind of, but if you look up close to it, you will see that there is actually a shift in colors. And then the star that is moving away will see its spectrum, not necessarily red. The star will still appear whatever color it is. So if it's a bluish star, it's going to appear bluish. But the entire spectrum, the spectral lines will move slightly toward red. Okay, how far they move, how fast they move, that determines all kinds of properties of that binary system. As a matter of fact, the formula that you use is this one. So what you do in this case, you take the distance between them. For the case of the Alpha Centauri A and B, they are separated by 23 astronomical units. So they're very, very close from each other. 23 astronomical is very, very small. I mean, that's what the distance from the Earth from the Earth, the Sun, which is the Earth, really, from the Sun to Uranus. So that's roughly about that distance. So it's very close. Two stars, big stars too, and they orbit each other every 80 years. They spin. every 80 years. So you can determine the period. You don't have to wait 80 years to get the data. Only a few days will be enough to determine everything else, okay? So now you have these two numbers, and if you divide the two, you're going to have the sum of the two masses. It turns out the sum of these two masses, you really have to have another technique to determine one of the masses. For Proxima Centauri A and B, they turn out to be, one of them is slightly about 10% bigger than the sun, about, not exactly. And the other one is about 0.8% of the sun. So one of them is slightly bigger than the sun, which means that it's going to live a little less than the sun. And the other one is actually a little less than the sun in terms of mass, which will mean that it's going to outlive its neighbor. Okay, so at some point down the road, you will have a white dwarf with a giant neighbor, which is a red giant, because by then this one starts to evolve to a red giant. And that is the picture that you're going to be looking at. That is, and next to them, there is Proxima Centauri, which is the closest star to us. So a three-star system, actually. Right now, they are a three-star system, and down the road, three-star. So the Proxima Centauri will not really be impacted by what's going on between these two stars. But these two stars, Alpha Centauri A and B, at some point, they will be in a binary system where one of them is a white dwarf and the other one is going to be a red giant. And that can lead to another problem that we're going to discuss down the road when you have binary systems like this ones. And there are kinds like this one that you will know. Actually, this one starts to feed off of the other one, starts to drag its materials until the white dwarf grows enough, and then something has happened, which is a supernovae. So anyway, right now they are circling around the center of mass. And how do you determine the center of mass? You use this formula, okay? So if you use this formula, now you have everything you need. So think about it one second. So the first one is the mass of the two stars. When you add them together, it's just the distance between them. So this is the separation between star 1 and star 2, A, cubed, divided by the time they spin. And again, as I was saying, you really don't need to wait 80 years, for example, for this star to get that number. So you get those two numbers. So you have the sum. Then you can determine their center of mass if you can somehow find where they are rotating about, the distance between this star, for example, and the center of mass, the barycenter. Then you know what the other distance is, because the sum is just the overall A that you measured earlier. So if you can find these distances, then this equation gives you the ratio of one mass over the other. So you will have, and this is for some of you who took algebra or taking algebra in here, the system, you can solve it 100%, because you will have two equations with two unknowns. These are the two unknowns. MA and MA are not known, MB and MB are not known, okay? So two equations with two unknowns, and you can solve. So basically, there is another technique involving the binary star system that can help us study more the stars. Now, think about it, what we did so far, okay? These two units. One of them, with the spectral lines, you can classify them and see their temperature and their properties. You don't know their masses up front, okay? It's just based on the spectral lines. But if you can take binary systems, and start to analyze them, analyze their motion, Doppler shift, and then you take that information and determine the masses, now you compare it to the spectral lines. So we're coming up now with a good model trying to build together. So we will know a lot of information based on the binaries, then we were going to make it true for the non-binary, for the solar stars that are by themselves, because why shouldn't they? So they're going to be the same classification. So the binary systems will help us build more knowledge about the stars. So now we know their spectral lines, we know their classifications, we know where they sit in terms of temperature, we know their masses, we know their radii, the sizes also, we know their compositions. We have a lot of knowledge. So down the road, we're going to build an HR diagram. An HR diagram, basically what it is just a picture where the stars happen to be, okay? You will see that most of them fall in only one line, or the main sequence. And then there are the odd ones, okay, the ones that are not on the main line. So where did they come from? That is going to emerge as a good visual for us to later on understand basically the history of the stars, how they form and where they end up. So we're building a lot of tools at this point based on what we know, trying to get to the point of how stars look like. Sounds good? Okay, thank you very much. Okay, guys, so I'm going to see you guys next week. And as I was saying, we will have the Thursday session recorded, and it's going to focus on the other 2 units. And again, please read the units. Do not rely on these recordings or the sessions. Make sure you read them, do the quizzes because they are really connected to those things. So make sure you do those and you follow until we finish these materials, hopefully in time, because there is a lot of content that needs to be also covered. So we barely started the stars right now. Thank you guys. And I will see some of you who are in group 1 for the lab. I will see you tonight. Those who are in group 2, I will see you Thursday. Those who are not doing the lab, I will not see you until the Tuesday of next week. Thank you. Thank you, Susan. Bye. Let me end the recording first.